In this video, we solve problem 2.2.21 from the Nagle Fundamentals of Differential Equations textbook, 7th edition. We're asked to solve the initial value problem, and here it is. We've got a differential equation right here and an initial condition when theta equals 0, y equals 1, and then we're given this. It says the solution is blank, and they give you a text box. The fine print says type an implicit solution. Type an equation using y and theta as the variables. So first of all, when we look at this differential equation, we have to decide which methods are appropriate for solving it. Now, since this is in section 2.2 of the text, you might think it's separable because that's the section when we learn about separable differential equations. And of course, you'd be right. But in general, if I'm looking at this differential equation and I'm trying to decide how to solve it, I just say to myself, is it possible to write this expression as a function of y times dy set equal to a function of theta times d theta? If you can write the equation like this, then it's separable. If not, you can't. And because we've got a function of theta times dy d theta here and a function of y times a function of theta over here, it is going to be possible to get all the y's on one side and thetas on the other. Now, one other thing that you should be wary of or cautious about is that when you are separating the variables, when you're getting the y's on one side and thetas on the other, you can't have a function of y plus dy or plus or minus dy or a constant times dy or a function of y times dy. It has to be a product. It has to be a function of y times dy. And we have to have a function of theta times d theta over here. Otherwise, it's not separable. Okay, so we're going to be able to get this in this form pretty quickly. Notice you have a dy d theta over here. If I want this to just be a dy, all I have to do is multiply both sides by d theta. It's because of the definition of the differential of y. Remember in calculus 1, if you had y equals a function of x, dy was defined to be that derivative times dx. That's how we defined the differential. Now this derivative in prime notation could just as easily be written this way, dy dx times dx. So we could use Leibniz notation instead. So because of this definition, it's almost like the dx's are reducing and then you're just getting dy over dx, multiplying both sides by dx gives you a dy. It's almost like that. It behaves like that, but you really don't want to think of it that way because this is really a function of x multiplied by dx, and this is really a function of theta multiplied by d theta. But if we take this and we do this, it's kind of like they cancel, and that's the definition of dy. So I've got a dy over here on this side and a d theta over here on this side. Now I want all the thetas on this side to go with the d theta, and I want all of the y's on this side to go with the dy. So I will multiply both sides by theta. That's going to get rid of this 1 over theta here. And then this y over y cubed plus 1, I really want that on this other side. So I will multiply by the reciprocal of that. Multiply by y cubed plus 1 over y. Okay, and now that we've done that, I know it's a little bit messy. These guys are gone, these guys are gone, the thetas are gone, and what we have on the left-hand side is y cubed plus 1 over y times dy equals theta times cosine of theta d theta. And I'll put that theta out front. And now it's in the right form. We've got a function of y times dy equals a function of theta times d theta. Now that we've separated our variables, we'll just anti-differentiate each side with respect to the variable on that side. Now, in this case, we don't actually have a rule for that. There is no quotient rule for antiderivatives, but this is just a monomial. I've got a polynomial divided by a monomial, so I can take that polynomial term by term and divide it by y. So this is the same as y cubed over y plus 1 over y, and y cubed over y simplifies. One of those y's will reduce, and now you've got a y squared. The antiderivative of y squared is easy. You just add 1 to the exponent and divide by the new exponent. Dividing by 3 is the same as multiplying by 1/3. And the antiderivative of 1 over y is natural log of the absolute value of y. Normally I would add a plus c, but I'm just going to put the plus c on this side instead. Now over here, when I want to antidifferentiate, I'll ask myself, do I have a basic rule for that? And I don't, because I've got a product. The next thing I might say is, can I use a u substitution? Well, I could let u equal theta, but then I would just end up changing all of the thetas into u's, and we would be in exactly the same place we are now. So letting u equal theta or letting u equal the variable will never work, because you're just changing one dummy variable for another dummy variable. And that's a term. I'm not insulting the variable. So okay, that u substitution is not going to work. So then we say, okay, what else do we do? If basic rules don't work and u substitution doesn't work and algebraic manipulation like we used on this side doesn't work, there's nothing to algebraically manipulate over there. Then we go for integration by parts. Now with integration by parts, part of this integrand is u. Everything else is dv. And then we fill out this little 2x2 table. The integral of u dv is u times v minus the integral of v du. U has to be something that you can differentiate, because in order to get from this side to this side, we need a du. V, or dv, needs to be chosen so that we can anti-differentiate it, because we need to be able to get from dv to v to get to this side. So with that in mind, usually we look at the integrand and we say, are there any natural logs? If so, that's your u. There are no natural logs. Are there any inverse trig functions? If so, that's your u. There are no inverse trig functions. In that case, most of the time, use the polynomial. So I'm going to let u be theta, which is our polynomial in theta, theta to the first, and then dv is everything else. Then we differentiate to get u, or du. The derivative of theta the derivative of theta with respect to theta is just 1. So du is 1 d theta. And then we say to ourselves, what's the antiderivative of cosine? So that's going to give us v over here. You differentiate here, antidifferentiate here, and that's sine of theta. You can always check what's the derivative of sine of theta? Cosine of theta. So that works out. And then according to our integration by parts formula, what we're going to get is u times v minus the integral of v du. So we have theta times sine of theta minus the integral of sine of theta d theta. And the antiderivative of sine of theta is negative cosine of theta. So I have a negative times a negative is going to be a positive cosine of theta there, plus a constant of integration. So this is our solution. They asked for an implicit solution in terms of y and theta, and I think that's it. If we differentiate cosine of theta, we get negative sine of theta, so that checks out. And then this over here we know is correct as well. But if you wanted to, you could differentiate this and get a common denominator, and you could show that if you take the derivative of this and simplify, you'll get this. And then we could differentiate this and simplify, and we could show that we get theta times cosine of theta. So we know that this satisfies this equation. So it's pretty easy. You just separate the variables and anti-differentiate, and then we get here. The hard part is remembering the techniques from Calculus 2 or Calculus 1 that will allow us to evaluate this integral and this integral. So this one just required a little bit of algebraic manipulation, and then this one turned out to require integration by parts.